consider some asymptotic measures related to the non-parametric tests. Actually, in non-parametric theory, the tests are not exactly obtained in terms of its distribution of test statistics. So, we shall find some asymptotic results for these test statistics. In this module, we first give a review of performance on comparison of estimation, and then we will give some idea on the comparison of hypothesis testing. First we go to the small sample comparison. In statistical point estimation, we compare two estimators through some expected distance measure from the parameter of interest. For example, suppose we have two estimators, one is T1n and other is T2n, and all are based on n observations for the estimation of some real valued parameter theta. Then the relative efficiency can be measured by the ratio of mean square errors given by expected value of T1n minus theta whole square divided by expected value of T2n minus theta whole square, provided the expectation exists. Naturally, the estimator with smallest MSE is preferable. If the estimators are unbiased, the above ratio reduces to the ratio of variances or the ratio of precisions. Then, in such situation, estimator with the smallest variance is the best. However, such a criterion depends heavily on the choice of the distance measure in addition to the existence of second order moments. Thus, we need another criterion known as Pitman measure of closeness, abbreviated as PMC, and this is defined by probability measure of T1n T2n given theta is equal to probability that modulus T1n minus theta less than probability T2n minus theta modulus. Then, in its simplest form, PMC measures the relative frequency with which T1n is closer than T2n from the unknown parameter of interest theta. However, PMC does not measure the relative distance of T1n and T2n from the true value theta, but calculation of PMC requires the sampling distribution of T1n and T2n, and hence is not easy to compute for a number of estimators. Now we come to large sample comparison. We assume that there are two consistent estimators T1n and T2n of some real valued parameter theta, and it means that T1n converges to theta in probability, and at the same time T2n converges to theta in probability. Sometimes it may go to theta almost surely. Since consistency is a desirable property for any estimation problem, rate of convergence would be a natural measure of relative efficiency. Thus, the estimator converging to theta in a higher rate is better. But the problem is that the rate of convergence is not easy to compute theoretically. However, if we assume the existence of MSE, then MSE of Tkn is equal to expected value of Tkn minus theta whole square tends to 0 as n tends to infinity, ensures consistency of Tkn for k is equal to 1 and 2. Thus, the rate of convergence can be judged from the ordering of MSEs, that is, the estimator corresponding to the smaller MSE converges at a faster rate to theta in probability than its competitor. In other words, if MSE of T1n is less than MSE of T2n for all theta, T1n is better in terms of the converging rate. But again, such a comparison involves huge calculation and hence lacks practical feasibility. Thus, we restrict to the class of estimators which are not only consistent but also asymptotically normal. That means we are concentrating on CAN estimators. That means consistently asymptotic normal estimators, and it is defined by the relation that Tkn minus theta has asymptotic normal distribution with mean 0 variance sigma square by n for some sigma k square for k is equal to 1 and 2. Then, as before, relative efficiency can be measured by the ratio of asymptotic variances. However, in this case, the efficiency is called asymptotic relative efficiency and it is abbreviated by ARE. In brief, suppose root over n into T1n minus theta converges to normal 0 tau square and root over n T2n prime minus theta converges to normal 0 tau square in distribution, where T2n prime is based on n prime is equal to n prime of n observations. That means n prime is a subsequence of n. Then ARE of T1n with respect to T2n is defined by small u12 is equal to limit of n tending towards infinity n prime n by n, provided the limit exists and is independent of the subsequence n prime. Thus, ARE can be interpreted as the relative number of additional observations required by the less efficient estimator to reach the same accuracy. Naturally, T1n is more or less efficient in the asymptotic sense if U12 is greater or less than 1. However, in actual practice, the limit is not easy to evaluate and we use the equivalent form U12 is equal to sigma 2 square is equal to sigma 2 square divided by sigma 1 square. So, we shall use this formula as a measure of relative efficiency, asymptotic, and it is called asymptotic relative efficiency of the sequence of estimated T1n relative to T2n. Next, we will come to the performance of comparison in hypothesis testing. Suppose we have two competing tests for the same hypothesis. Then it is natural to inquire about the relative performance. In estimation theory, we have used some distance measure to measure the performance. In hypothesis testing problem, the only relevant measure is the power of the test, that is, a bounded measure of departure from the value specified by the null hypothesis. Thus, if the tests are of same level of significance, then the test having a power curve lying above the power curves of all the competitors would be preferred. However, in non-parametric inference, the underlying distributions are never specified and hence construction of optimum test is almost impossible. Therefore, at a minimum, we can compare the power function for fixed sample size, but such a comparison depends on the sample size. The alternative, the form of the underlying distribution and the level of significance. Hence, reaching a general conclusion will be difficult. Therefore, as an alternative one, we can use the large sample methods to compare the tests. Although use of large sample of approximation eliminates the dependence on sample size but creates a more serious problem because we in general consider consistent tests so that power reaches unity for large sample sizes. Thus, the limiting power function is of no use for the purpose of comparison. Pitman in the year 1948 in this context suggested to compare asymptotic value of power considering sequence of alternatives converging to the value provided by the null hypothesis. An approximate choice of the sequence of alternative enables to clear comparison. First we come to the finite sample efficiency. Suppose x1, x2, xn are IID observations from an unknown distribution function g, and our interest lies in testing h0 that g belongs to a subclass of the class of all possible values of g, and we denote it by omega naught against an alternative ha that g belongs to some subset omega a which is disjoint to omega naught. Consider two different level alpha tests denoted by phi n upper 1 and phi n upper 2. That is, for any k is equal to 1 and 2, expected value of phi n upper k under g is less than is equal to alpha for every g belonging to omega naught. Take an arbitrary g star belonging to omega a and fixed beta such that alpha less than beta less than 1. If capital Nk denotes the minimum number of observations required by test k to exceed a prefixed power beta, then the relative efficiency of test 1 with respect to test 2 is the ratio of the required sample size to attain power at least beta. Precisely, if Nk denotes the minimum number of observations required by the test k to satisfy expected value of phi nk upper k under g star greater than is equal to beta for any k is equal to 1 and 2, then the fixed sample relative efficiency is defined by the ratio E12 of alpha beta g star is equal to N2 of alpha beta g star divided by N1 of alpha beta g star. Naturally, test 1 is preferred over test 2 if E12 is greater than 1, and if the opposite holds, we prefer test 2 to test 1. Next we come to asymptotic relative efficiency, which is abbreviated by ARE. Now E12 depends on alpha, beta and G star, and hence, as discussed earlier, makes the comparison difficulty. Thus, before defining the asymptotic relative efficiency, we discuss the concept of local alternatives and asymptotic power, and that asymptotic power is abbreviated by AP. Assume that the underlying distribution can be indexed by a real parameter theta so that the problem reduces to testing of H0 that theta belongs to omega naught against HA that theta belongs to omega A. Then a sequence of alternatives theta n is called Pitman's local alternatives if number 1, theta n belongs to omega a for all n greater than is equal to 1, and number 2, if theta n tends to theta naught belonging to omega naught as n tends to infinity. Now consider a sequence of tests phi n for testing h naught that theta belongs to omega naught against ha that theta belongs to omega a. Then phi n is asymptotically size alpha if expected value of phi n under theta tends to alpha for all theta belonging to omega naught. Then the AP of phi n against the local alternative theta n is defined as limit n tending towards infinity of expected value of phi n under theta n provided the limit exists and it lies in the open interval alpha 1. However, determination of AP is not straightforward and hence we provide below an equivalent expression considering some assumptions. Consider a sequence of asymptotically size alpha right tail test phi n based on statistic Tn for testing H0 against HA that H0 and HA already have mentioned. That is, phi n is equal to 1 if Tn greater than Cn and 0 for Tn less than is equal to Cn, where Cn is a sequence such that expected value under theta of phi n tends to alpha for all theta belonging to omega naught. Then the AP of the sequence phi n against the sequence theta n is given by beta is equal to limit n tending towards infinity of expected value of phi n under theta n which belongs to alpha 1 open interval provided the limit exists. Now we assume some further regularity conditions. Whenever we go through exact comparison or exact performance of the test, we will find some exact result. But if a test is consistent, then its asymptotic measure, that means its power in the long run will become unity. So we cannot use the fixed alternative for testing such problem.